let's say we want to estimate change in y from x is equal to 1 to x is equal to 1.1 for y is equal to x cubed. Let me draw out what I'm talking about. Let's say we have a graph of y is equal to x cubed going like this, and we can evaluate this function at x equals to 1, which should get you an output of 1 because 1 cubed is 1. And we can also, obviously this is not to scale, we can evaluate the function at 1.1, and that should get us some value, this value. And we wish to, well, what is delta y? What is change in y? That's the change in the function value, or the vertical change from this point to this point. So that's delta y. But we do not want to find delta y, because finding delta y is not easy to do. You have to do 1.1 cubed and subtract it from 1 cubed. Okay, arguably this is not too bad, but if you have a function y is equal to x to the 7th plus cosine of x sine of x plus sine of 2x plus e to the 2x, and they ask you to find delta y from x is equal to 1 to x is equal to 1.1, now this thing gets much more complex. But I want to start with an easy example and show you one way that we can estimate this change in y using a concept called differential. And I'm about to show you what that is. So we wish to estimate this delta y, and the way we are going to think about is we are going to use tangent line approximation. So let me redraw the function. Let me draw a close up view of the function. This is going like this, it's going up. We evaluate the function at 1, we get this point, and we evaluate the function at 1.1, and let's say we get this point, and we want to find the change in y, so we want to find this. Okay, if we draw a tangent line through the point 1, so the tangent line is going to go something like this, and we know how to find the equation of a tangent line. Since we know the point that it's going through, all we need to do is find the slope of the tangent line, which we can by differentiating function y is equal to x cubed and evaluating that f prime of x at x equals to 1. So we know how to find the equation of the tangent line, and we can plug in 1.1 into the tangent line, and that's going to get us this point. That is going to get us this point right below this red point. Right below this red point. So this point is giving us an estimate of f at 1.1. This is giving us an estimate of 1.1 cubed. So the change in y, the estimate of change in y, we attempt to get from this tangent line approximation is this blue distance. And how we call this blue distance is by using dy. And we call the change in x dx, and that's all the differential is. Dy is differential of y, and dx is differential of x, and that's all that is. Differential of x. Differential of x is basically the same thing as change in x, and we just use dx when we are using the tangent line to specify it's a tangent line, not just change in function. And dy is telling you the change in the tangent line from some value to some value plus dx. It's giving you an estimate. So dy is an estimate of delta y. So that's what differential is. So let me attempt to use this differential to estimate our function at 1.1. What is the equation of the tangent line? Well, what is f prime of x? F prime of x, since f of x is x cubed, is going to be 3x squared. So what's the slope? What's the slope at x equals to 1? That's 3 times 1 squared, which gets you 3. And we know the tangent line is going through the point 1, 1. So we know the equation of the tangent line is y minus 1 times 3 times y minus 1 is equal to 3 times x plus 1, or y equals to 3x minus 2. So we know that is the equation of the tangent line. So using this equation of tangent line, we can approximate we can approximate our function value at 1.1, which is going to be 3 times 1.1 minus 2, or 3.3 minus 2, or 1.3. So that's the estimate we are getting from this by using this equation of the tangent line. And what is dy? What is dy in this case? Well, dy is change in y in the tangent line, so that's going to be 1.3 minus 1, which is 0.3. Another way of getting dy, maybe you realized, is by multiplying our derivative of our function at 1 by dx. That is the value of dy. And the reason is f prime of 1 is the slope. That's the slope of the tangent line, the green line, that goes through our graph at x equals to 1. And the slope is telling you how much y is changing for this tangent line per one change in x. So if the function is changing by dx, then the y for the tangent line is going to change by the slope times the dx. So that's one way of finding dy, and sometimes dy is defined as f prime of x dx. So differential of y is defined as f prime of x dx, because that's one way to find it. Let me show it to you. So dy is equal to f prime of 1 dx. F prime of 1, as we found, was 3, and dx is 0.1. That gets you 0.3, which is also the answer we get when we subtract 1.3, when we subtract 1 from 1.3. So, how close is our approximation? What is the actual value of 1.1 cubed? Let's evaluate that. 1.1 times 1.1 times 1.1 gets you 1.331. 1.331. So our approximation was pretty close using our tangent line approximation. And again, the differential dy is an estimate of delta y, the actual change in the function, using the tangent line approximation.